Back. Happy New Semester, Happy New Year. It's my great pleasure to introduce our first seminar speaker of the new year, Anil, Seth. So Anil and I share something in common, which is that we are both from Lincoln, Nebraska. He is a proud Lincoln High Link, whereas I, of course, am a proud Lincoln North Star Gator. After that illustrious start, he got his PhD at the University of Washington and then spent a few years as a CFA fellow at the CFA. Before joining the University of Utah, where he's been now for, I think, about 10 years-ish. Greater 10 years-ish. So he's a longtime user of, in particular, SDSS, and is a big expert in understanding the formation of star clusters, which we'll hear a little bit about today. So I believe we're full on dinner, but if you are really eager to go, beg me, and we'll see. I'll kick somebody else off who doesn't bribe me as much. Otherwise, I will let Anil take it over. So,
thanks for having me here. I am going to be telling you about galaxy centers today. And this is our main character of the show, but we're going to meet it later. And first, I'm going to kind of talk to you more generally about the centers of galaxies. So if we go to a typical nearby galaxy, and this was one of the galaxies that I worked on in my PhD thesis and what got me interested in the centers of galaxies in the first place. And we look at a nice high resolution image of that galaxy. You can see lots of individual resolved red giant branch and massive young stars. And then at the center of this galaxy, you see a football-shaped object. And that object is actually a really, really massive star cluster. And you can see that it looks kind of, it's not perfectly round. This thing has a density, a stellar density that's about 1 million times higher at its center than the underlying galaxy disk. So it's a very distinct, massive component. And nuclear star clusters like this are located in most galaxies. Now it's almost 5-6 years ago, my collaborator Nadine Neumeier and I and Torsten Boker wrote a review on these nuclear star clusters. And you can see here, this is a plot that shows galaxy stellar mass and then the fraction of galaxies that have a dense massive cluster at their center. And these galaxies, you can see that over kind of a wide range of galaxy masses, more than half of galaxies have these really massive star clusters at their centers. And these clusters are typically more massive and denser than globular clusters. And so they tend to be they're the most massive dense stellar systems that we know, the densest stellar systems that we know of. And you can see here, they correlate, the mass of the nuclear cluster correlates with the mass of the galaxy that it lives in. So more massive galaxies have more massive nuclear clusters. And so the reason, why these things exist, we have a little bit of a sense of a couple different ways that we could get these nuclear star clusters. One is through dynamical friction of massive clusters. So dynamical friction basically means that as a massive object is moving through a galaxy, all the material piles up in its wake, acts as a drag force, and gradually that drags sources into the center of the galaxy. And so you can get multiple massive clusters merging together to form these nuclear star clusters at the centers of galaxies. But of course, the same thing can happen to gas. It can lose energy, get brought to the center, and form stars directly in place. And over the last 5-6 years, we've really identified that there seems to be a transition where at the lowest mass galaxy end, the clusters seem to be primarily built through this globular cluster in spiral. Whereas at the high mass end, it seems like the in situ formation, meaning the gas that accreted into the center and then formed stars, is the primary way that the more massive galaxies are forming their nuclear star clusters. So we know quite a bit about nuclear star clusters, partially because they are bright and we can study their spectra and all of that stuff. The Milky Way is no exception to having a nuclear star cluster. This is a pretty famous Spitzer image of the central regions of our galaxy. And you can see that this object in the center here is the Milky Way's nuclear star cluster. It's about 30 million solar masses. Its effective radius is a few parsecs. So it's really, really much, much bigger than like the most massive cloud cluster in Milky Way is about 3 million solar masses. It's about 10 times that size, 10 times that mass, similar size. And if we zoom right into the center, of course, this is the part that you're probably most familiar with. We see a handful of very bright stars. How many people have seen this movie? Okay, almost everyone. Okay, I'll play the movie. So these bright stars are orbiting around a radio source, Sagittarius A star. And these are actually massive young stars. We're really lucky that these stars exist. If we had lived 10 million years ago, there is not a comparable population of stars that are 10 million years old. These are all really young stars. So we live in a lucky time. And there's these really bright stars that are orbiting around, massive young bright stars that are orbiting around our central black hole. And these are moving, the two that have completed these orbits here have orbital motions of around 5,000 kilometers per second. So, for contrast, we're moving about 30 kilometers per second around our sun. So that means that there's a lot stronger gravity there, and the inferred black hole mass is about 4 million solar masses. The scale of these is, kind of bigger than solar system, but not by a lot scales that these orbits are on. So 4 million solar mass black hole sitting at the center of this nuclear star cluster in our Milky Way. And so this is a pretty typical setup. We have these dense star clusters, and at their centers, we have massive black holes. And those are what I'm going to be talking about for the rest of the talk.
So are these stars part of the bigger nuclear star cluster? Or
yeah.
It continues all the way in?
Yeah, so the nuclear star cluster, the nuclear star cluster isn't a single-aged object because it continuously is forming stars. And this is, there's within the central about half parsec, there's a population of young stars, of which these S stars are a member of that young star population. And they're B type stars. And yeah, so they are part of the nuclear star cluster. Okay, so black holes, many of you know lots about these here, but black holes we've known about for a long time. And this famous picture of the M87 black hole illustrates a couple interesting things. One, black holes have jets. Those jets can feed back on our environment. We also can resolve the sphere of influence, the event horizon of the black hole using the HT. And so these play an important role in galaxy formation because they're the most efficient way to turn mass into energy. That means they can feed back negatively on a galaxy as they're accreting and limit and regulate star formation in those galaxies. And so that they play this important role in lots of current exciting JWST results about black holes accreting at high redshift that we're seeing. And yet, despite that, we really don't know how they formed. We don't understand what is the formation mechanism. We know in low mass black holes, they form from massive stars exploding. We don't have that equivalent picture for supermassive black holes. We don't know what their progenitors were. So this is a very cartoon drawing of the number of black holes that we have found in the universe through various ways versus their mass. And you can see there is a big gap in this distribution. There's these stellar mass black holes that we understand the origin of, and then there's massive black holes or supermassive black holes that we don't really understand the origin of. And the question that we don't know exactly the answer to is, are there any of these intermediate mass black holes? And there's lots of people trying to answer this question in various ways. And we'll see a good example later in the talk of at least one black hole that exists at this mass. But for the purposes of why I'm talking about this now is it's possible that the formation mechanism of black holes is linked to this gap. Maybe the supermassive black holes form very massive. And the reason why we don't have intermediate mass black holes is because there's no mechanism to form them. Alternatively, maybe there are lots of them, and the reason why we haven't found them is just a selection effect. So that's what we'd like to understand. So these intermediate mass black holes play an important role in us understanding this formation mechanism of massive black holes in general. This is a figure from Mara-Mezcua. The y-axis here is redshift. There's some different possible mechanisms for forming black holes at high redshift. The kind of favored mechanisms, you could just have population 3 stars, the very first stars in the universe, could leave behind fairly massive remnants. Those remnants could grow over time. An alternative scenario is that they directly collapse to, say, 100,000 solar masses, and those have to grow a lot less. There's a lot of JWST observations right now that suggest that, or at least people are interpreting them as evidence that direct collapse black holes must exist, because to grow them in the time period between when they observe them in the beginning of the universe is very challenging otherwise. So there's also some other mechanism. You could, for instance, nuclear star clusters themselves could provide a mechanism through the fact that they're so dense. You could have stellar mergers before things blow up, or post facto, you could have black hole mergers that open up in INDH, like through gravitational wave mergers, the things we observe with LIGO. And in fact, the most massive black hole on the kind of stellar mass black hole and is about 150 solar masses and is from the merger of probably a multiple merger system of multiple black holes merging together over time. So you can kind of see that if black holes originally formed at lower masses, then some black holes shouldn't grow into supermassive black holes. There should be leftovers, and those leftovers should be observable in today's universe. And so that's what a lot of what I've been working on is trying to find those intermediate mass black holes. So a lot of my work over the last 15 years or so has been making dynamical black hole mass measurements. This is something that I know many of you in the audience are experienced in, but the basic idea is just that we use high resolution images to create a stellar mass profile. And then we use that stellar mass profile to predict what the motions of the star should be in that object. And then we measure the motions of the stars at hopefully also high resolution. And then by comparing that to the model with and without a black hole, we can establish whether there's missing mass there or not. And so my group has worked on this for a long time. And we found that black holes are common in galaxies down to about 10 to the 9 solar masses. So here are all galaxies that we found black holes in. And we found the first dynamical detections of black holes below 1 million solar masses. And this is work by my first grad student, Yu Nguyen, and Mark Denbrock, Tim Davis, and not in my group, but did publish some of this.
Sorry, Ani, can I ask a question about that? So
Yeah.
say 5 to 50 times lower, is that the mass of the galaxy or the mass?
Yeah, the stellar mass of the galaxy.
The mass of black holes are still consistent with like the Milky Way, except for the first dynamical one below 1 million, or?
Yeah, so these are almost all of them are below 1 million solar masses that we found, but they're not scaled down by 5 to 50 times. Yeah, right. They're less than that. But the Milky Way, it turns out, is actually a pretty low mass black hole for its stellar mass. Andromeda has a black hole that's 100 times bigger in essentially the same mass galaxy. So these nuclear star clusters that I started talking about in the black holes, they coexist in many galaxies like our Milky Way. And that is of great interest to me. I think that there's definitely a possible link between the formation, and we'll get into that a little bit more, but the formation itself may be tied to the formation of these supermassive stars and near-mean mass black holes. So the fact that there is a black hole at the centers of these nuclear clusters might not be a coincidence. It might not just be due to dynamical friction pulling both in. It could be that they're causal. And then there's also consequences of their coexistence, which is that they interact with each other. So the stars from the nuclear star cluster will fall onto the black hole sometimes. And when that happens, you can get tidal disruption events. These tidal disruption events are bright flares, kind of supernova luminosity flares. as the star becomes unbound and accretes onto the black hole. And this is really exciting because transients are what the Rubin Observatory is trained to find. And there should be, potentially we have about 100 tidal disruption events that we found so far. And Rubin may find 10 a night or maybe even more than that every night. So it's very exciting. And one of the things that I have a student working on right now is trying to predict how many tidal disruption events should happen in low mass galaxies from these from stars from the nuclear cluster falling onto the black hole. And this is from his paper, Christian Hanna, who just finished his PhD in December. And this is showing for a sample of nearby galaxies what the TD rate is as a function of galaxy stellar mass. So you can see there's this kind of peak around 10 to the 9.5 solar masses, and then the rate goes down at the lower mass end, and at the higher mass end, there's a lot of scatter too in that relationship. The gray bands are showing the intrinsic scatter. And so we're trying to build models that will predict with different amounts of different demographics of black holes in low mass galaxies, how many tidal disruption events should we see in those galaxies? And hopefully we'll be able to then use Rubin constraint. Another interesting thing is that in the most massive galaxies like M87 that I showed earlier, there are no nuclear star clusters. And we think that's also related to this coexistence with black holes. And if two black holes merge together, they essentially scatter out all of the stars in the central region of the galaxy and destroy the nuclear clusters. So we don't see them there. Okay, any questions before I keep going on? Yeah.
So for the TDs that you find with Rubin,
10 to 100 a
Sounds
night
like a
is
lot.
what is there's a paper that suggests we'll find 10 to 100 a night.
Oh, okay. I was gonna say, is that like just from Rubin alone or like post follow-up? Because I know sometimes they can look like EVNs.
Yeah. I mean, so that number is just how many should be detectable,
Okay.
not how many will be detected. So the job is, of course, actually detecting the ones that exist. And that's a harder proposition. And there's a lot of smart people working on this, but I think initially my guess is that we will definitely not find that many number. And that hopefully over time we'll build up with the samples of things that we see, we'll be able to build up better filters that allow us to find a larger fraction of all the TVs that are potentially visible. Galaxy centers are bright places. They're hard to find things in. There's lots of variability from AGN. Supernovas that happen to be blowing up right in the centers of galaxies. Yeah, there's a lot of, yeah.
In my mind, I can come up with a lot of explanations for why there's that turnover.
Yeah.
Something to do with the number density of stars in the center of the galaxy versus the number of stars or something.
Yeah.
You guys have a model for it, so why?
Yeah, this is just an empirical model. That's great. The line is an empirical, but the reason why this happens, I mean, this is a calculation based on the density profiles of real galaxies.
Okay.
And that's what, that's the work that Christian did, is he calculated nearby galaxy density profiles all the way to the center, then use that to predict the tidal disruption event rate using dynamical models. What's going on here at the high mass end is that stars, as the velocity dispersion goes up, the stars are less and less likely to interact with each other. And so you end up getting fewer and fewer perturbations on the stars into what's called the loss cone. And that means that you don't end up getting as many tidal disruption events, even though the cross-section of black holes is way bigger in those galaxies.
Right. So either the number density is higher, they're moving too fast with interactions to get them near enough to the black hole.
Yeah, that's right. And at the very highest mass elliptical galaxies, these things are cored. They're like M87, and they don't have low rates because of that. Yeah. Okay, so that's all. That's kind of like the background information. And now we're going to move into stage 2 of this story, which is that not all nuclear star clusters stay at the centers of galaxies. So we know that galaxies interact. This lovely image is of 2 galaxies that might be at the same distance in the Virgo cluster. And then superimposed on that is a movie of a 10 to the 10 solar mass galaxy falling into this giant elliptical galaxy. And what you can see is that, as it goes through the center of the galaxy, tidal forces unbind the stars from the galaxy, and through the magic of simulations, this thing ends up at the location of that little dot down there. And that little dot down there turns out to be what we call an ultra compact dwarf galaxy, or it's actually really just a really big, massive star cluster. And what we think this thing is just a nuclear star cluster from the galaxy that's left behind because it's so much denser than the rest of its galaxy that even those tidal forces can't ever pull it apart. And so even after a galaxy interacts with like, for instance, Sagittarius is interacting with the Milky Way right now, its nuclear star cluster is a Messier object, M54, and it won't get destroyed. It'll keep orbiting around in our galaxy. So we think that these nuclear star clusters survive this tidal stripping and are probably living on in the halos of our galaxies. And these objects turn out to have black holes in them as well. So this was, that object I just showed you was this M60 UCD1, which was the first one that we found a dynamical black hole mass in. You can see here, this is kinematic data from Gemini of that object, and you see this very sharp dispersion peak at the center that's indicative of a massive object making the motions of the stars really fast there, just like in the center of our own Milky Way. This thing actually has a 20 million solar mass black hole in it, even though it's about a 100 million solar mass cluster. So something like 15% of the total mass of the object is in this black hole. So it's very unique in that way. It turns out it's not unique. There's actually, in all of the very massive UCDs that we've looked at, we've also found evidence for black holes in them. And we think that in those objects are unlikely to ever be ordinary star clusters. We think essentially all clusters that are above about 10 million solar masses are likely these stripped galaxy nuclei. Okay, so that brings us to Omega Centauri, our main character for the day. This object is the nearest galaxy nucleus to us. We're pretty sure that this object was once the core of a dwarf galaxy that then fell into the Milky Way. The reason we think this is that it has a very wide range of chemical abundances. It's metallicity, spreads over more than an order of magnitude. And we don't see that in typical globular clusters. Globular clusters don't have escape velocities that are high enough to retain supernova ejecta. It's very hard for them to have large spreads in metallicity. So you can see here there's this really large spread in metallicity, and then what galaxy it was the center of is a little bit more controversial, I would say. I think most people agree that this is likely a nuclear star cluster based on its properties, but what it was the center of is a little bit more controversial. It is, I would say most people agree that it was probably the core of the Gaia Enceladus sausage, which is like a horrible name, but that's likely the largest contributor to our Milky Way, the single largest merger in our Milky Way's history. And this is an energy angular momentum diagram. You can see Omega Cen is here, and it's actually at lower energy. It's counter-rotating. The lower energy is expected because of the dynamical friction over time. So it's sinking to the center of our Milky Way. And so that's what makes it kind of challenging to link. But we have actually an upcoming paper that I think establishes that link a little bit more strongly. Okay, so my closest collaborator, Nadine Neumeier, who's a group leader at MPIA, and I, about 5 years ago, started this project OMEGACat. And the idea was to study the center of Omega Cen as the nearest nuclear star cluster to really understand its formation history. We combined Hubble data and data from VLT-MUs, 100 pointings of VLT-MUs across the center of this galaxy. And there's some fantastic people who've worked on this. The initial catalogs, the HST astrometry was done by Max and Selena, did the Muse spectroscopy. These are both MPI students. My student, Callie, who's now a postdoc at MPI, worked on star formation history, and I'll be presenting results from all these folks, and Primordial as postdoc working with me. on the abundances of stars in this cluster. I have some cool data movies here. So here is our Muse mosaic. So this is 100 separate pointings of Muse, 300,000 stars. For each of those stars, we of course have its luminosity and color, but then we get spectra, and you can see here's two stars that have the same brightness, similar signal noise, but you can see this right-hand star has much more abundant lines, and that's because it's a higher metallicity star. So we're able to derive the metallicity for each of these stars, and we get, you can see this beautiful, now these are colored by the metallicity inferred, and you can see a very clear sequence. And the redder the star is, the more metal rich it is. Data. So that's the Muse data. The Hubble data, this was stolen from an XDF video that this is the full catalog of Hubble Space Telescope observations of the center of Omega Centauri. And it turns out that Omega Cen was used as the calibration target for the WIFC-3 camera. And it keeps looking at it to see, like, are the stars still the same brightness? Yes, check, like we've got our calibration. And so every image you see here, there are over 1,000 images of this central region. At the very center, there are 500 separate images. So really unique data set. It's one of the most imaged places in the sky. And it has a very nice long time baseline as well. And so this means that we can derive proper motions for many stars. We have proper motion measurements. Max Haeberle, who's now an ESO fellow, derived 1.4 million proper motions for the stars within the effective radius of Omega Cen. And the accuracy of the velocities for brighter stars is about less than 1 kilometer per second. And so the velocity dispersion is about a factor of 10 higher than that, than our errors. So we're really well resolving the motions of individual motions of stars within this cluster. And the number of epochs at the center is about 500 separate observations of each star. Okay, so I'm going to tell you about some fun stuff that we found with OMEGACat. The first is hunting for a massive black hole. Then I'm going to talk about a little bit of Omega Cen's formation history. Talk about the dark matter binary populations. And then there's a couple things I won't talk about at the bottom there. Okay, so for those of you who don't know, there's been a lot of controversy about whether there's a black hole at the center of Omega Cen. Eben Oyola, just up in Austin, wrote this paper in 2010 and said, yes, there is an intermediate mass black hole based on our kinematic data. And using the kind of method that I outlined earlier, its mass is 47,000 solar masses. And at the exact same year, when Roland Vandermarle and Jay Anderson wrote a paper and said, no, there is no black hole. The upper limit on the mass of the black hole is 12,000 solar masses. And our kinematic data, which was different data, does not support there being a black hole here. So there's a couple reasons why this is a hard measurement. One is it's not actually straightforward where the center of the cluster is. When you take a large scale image, you can see, okay, yeah, the center is somewhere here. But these later images, if they weren't, the center wasn't the middle of the image, you wouldn't know, right? You couldn't tell if the center was here or here. I can convince you of that, right? And that is a significant complication because, of course, you want to be able to put a model at a specific point. You want to say, okay, the black hole is at the center. What does that mean for the kinematics? And so that was one of the main reasons the two different papers used two different centers that were offset by 10 arc seconds from each other. And the second complication, there's more than two, but the second complication is that there's been an interpretation issue, which is that when we look in dynamical models, what we're looking for is dark mass that doesn't follow the same profile as the light in the cluster. And that doesn't necessarily have to be a single massive black hole. It could be a whole bunch of stellar mass black holes. And in the modern era, people have realized that actually many black holes, of course, were born in the formation of a cluster, and evolutionary models of outer clusters now support there being a large population of black holes living to the present day in those clusters. And if those black holes actually mass segregate to the center of the cluster, and the center means like maybe the central parsec or so, and it becomes very hard to actually tell the difference between those two in a dynamical model. So this is from a paper by Holger Baumgart in 2019, 2 figures. And the black points are the data. The red points and blue points are an IMBH. The blue one is an IMBH, and the red one is stellar mass black holes that have mass segregated to the center of the cluster. And they've retained 75% of black holes that were born. You can see in the velocity, this is the velocity dispersion here versus radius, but those two predictions are very, very similar. So you can't really tell the difference. This is the central region, just the central 20 arc seconds of the cluster, and it's a line of sight velocity distribution of the stars. So you're getting, rather than just boiling that down to a single number, the dispersion, you're looking at the detailed distribution. And you can see there's a big difference now between the blue and the red lines. In the red line, where there's lots of stellar mass black holes, you don't have any stars that are moving faster than the escape velocity of the cluster. Any star that's moving faster, the escape velocity of the cluster just leaves the cluster. And whereas in the intermediate mass black hole case, you end up having stars that are close enough to the black hole that they're in a deeper potential and the escape velocity is higher. And so there's a clear signature there. And you can see that this earlier data strongly supported the stellar mass black hole scenario. And so from this paper, they concluded, no, there's no IMBH in Omega Cen. Instead, there's a whole bunch of stellar mass black holes. So these fast stars are really the signature for an intermediate mass black hole. They're kind of the smoking gun that we expect for a black hole. So when Max made his catalog of 1.4 million proper motions, he said, okay, I'm just going to look at every star that is moving faster than the escape velocity of the cluster. We have an estimate of that. It's about 60 kilometers per second. And where are they? And it turned out there was a whole bunch of stars, 7 of them, in the central few arc seconds close to the center that was identified by Anderson and Vandermarl, the paper that didn't find a black hole. This is a zoom in of that section. You can see they're all oriented in different directions. And these stars are from proper motions that arrived over 20 years. So here is what the fastest moving one looks like. It's moving at almost twice the escape velocity. And we have this beautiful data of many data points moving from the bottom right here to the top left. See, it's moving basically in a straight line. And this is what it looks like on the detector. It's moving, this pink line is the same in each figure. And the star is the centroided location of the star, and it moves about 2 pixels over those 20 years. 2 pixels over 20 years gives us 113 kilometers per second. So of course, the first thing we wanted to do is understand, you'll notice in this figure, there was definitely some fast moving stars at larger radii too. This star isn't alone. And the reason why there's fast moving stars at larger radii is because if a star is located between us and Omega Cen, it can look like it's moving really fast just because it's close to us, or it's moving at a different potential. So we expect foreground stars to be present in this cluster. And so we just look at the number of fast stars as a function of radius, and you can see that at about 0.003 stars per square arc second is the level that we see at large radii. And that turns out to be identical to the prediction from a Besenstein model, which is a model Milky Way galaxy that has kinematics. And so we think that this is just an accurate measurement of our Milky Way background. And then we can take that background level and see how likely is it that we have these 7 stars sitting at the center of the cluster. It's actually, there's 5 that are more than 3 sigma from the escape velocity. And the chance of that is 1 in 100 million. So these are not Milky Way foreground stars. And so our interpretation is that these are stars that are bound to an intermediate mass black hole. And we can use the velocity of those stars as a minimum to the mass of the black hole to keep those stars bound. If they weren't bound, they would leave the cluster within a few thousand years, and we wouldn't see them. And we'd have to actually deplete the entire cluster to have that rate of outgoing stars. So, of course, the position of the black hole is not known. So we've chosen the position that minimizes the black hole mass. And when we do that, we get a minimum mass of about 8,200 solar masses. So this is firmly in the IMDH range. We get an upper limit of about 50,000 solar masses based on the lack of lots more fast stars. So we can compare to simulations and get an upper limit on the black hole mass of around 50,000 solar masses. So this is, for me, this has been, I think, the most exciting result that I've had in my career. Really, I'm really excited about it, that I've been involved in. This is, people have been looking for intermediate mass black holes for a long time. The previous best candidate was an X-ray source in a galaxy 100 megaparsecs away. It's very hard to study in detail. And this is the strongest evidence for an intermediate mass black hole that we have, I think, in any system. It also is the nearest massive black hole to us. And it's the second massive black hole with multiple bound companions. So you can see here, the gray stars are a snapshot of the stars at the center of our Milky Way. And you'll notice this is the same physical scale. It's in parsecs. So these stars are on the same physical scale as those stars at the center of our Milky Way. The difference is I've drawn vectors on here. Those vectors are different by a factor of 10 in the length that they're showing. And that's because this black hole is about 100 times lighter than the black hole at the center of our Milky Way. And so the vectors are a factor of 10 smaller. The velocities go as square root of the mass. So we have a comparable scenario to the center of our Milky Way, but with a much lower density system of stars than we have at the center of our Milky Way. That was why I was saying we were lucky to have that situation at the center of our Milky Way. Okay, so we have a lot of ongoing follow-up. We got a very deep JWST near spec observations of these stars. They're so faint that we don't have any radial velocities despite our MUSE data. So here is an example of the fastest moving star here and a velocity determination for that. That was taken this last summer. This data, we're still working on getting that published. We also had ALMA data taken. We were hoping to discover the accretion counterpart of this intermediate mass black hole. This black hole is the faintest black hole we know of in the universe. It's at less than 1 trillionth of the Eddington rate. So it's accreting at less than 1 trillionth of its Eddington rate. It's about a factor of 1,000 fainter than the Sagittarius A star. It's at about a 1 billionth or 100 millionth of its Eddington rate. So this is a really, really faint object. There's apparently no gas around, or for some reason that gas isn't efficiently accreting onto it. Unfortunately, our ALMA data also is a non-detection. So it'll get published somewhere, but it's not super exciting. We also have JWST astrometric follow-up, and our goal is the previous motions that we have are really consistent with being a straight line. There's no curvature to them at all. And we're hoping that with higher signal noise of these faint stars, we'll be able to detect accelerations in the stars. Accelerations will point towards the black hole, and they can also help us constrain the black hole mass. And then we're also working on dynamical modeling. One thing that I'm doing is working on a kind of novel method of dynamical modeling that just models the fraction of stars that are moving faster than the escape velocity of the cluster without a black hole. those are the signal that most definitively tells us about a black hole. And when we do that in Omega Cen, we get a mass of about 30,000 solar masses for this black hole. And that should be coming out soon. Any questions on this? Yeah.
How do you compare to the original claims for the black hole? I try to remind myself a little bit of the masses were. One with the upper limit, the other one was from.
Yeah.
And how do the centers compare? That's right. The center that minimizes the mass. They kind of resolve their discrepancy, or
yeah, they never resolve their discrepancies. I would say that the Noyola paper is not. The black hole is located 10 arcseconds offset from where we find the fast-moving stars, and so its mass might be consistent with our data, but its location definitely is not. So I would say that kind of doesn't suggest that that was a correct modeling. I think part of what happened there is they took the velocity dispersion peak as their center, and so there's a little bit of a selection effect there. The van der Marel paper that had the upper limit, their center is right at the center of our group of stars, and they had very carefully determined the center using star counts. So it is. I would say it's the best determination of the center that's been done so far, and we find their upper limit is marginally consistent with our detected black hole. But it turns out that this is one of the subtleties where I said there's more than two complications. The Omega Cen's profile is really flat, and that means its intrinsic 3D profile is also very uncertain. So the fraction of stars that we see along the line of sight at the center of the cluster, the ones that are actually in 3D close to the center are less than 5% of the stars. Most of them are projected along our line of sight. And so this is why dynamical modeling is really hard in this situation, because the stars that would give you the signal are just a tiny fraction of all the potential stars along that line of sight. And that isn't as much of a problem if the profile is peakier, because then more of the stars are close to the black hole and you're actually getting an increase in the velocity dispersion like you typically find in the effective cases. So I think the fact that they got an upper limit isn't that surprising. It turns out that the other thing that's weird is that this is it's like a 99% confidence result, is that the stars are fainter than the stars in the cluster overall that are at the center. These fast-moving stars are fainter, and I think there's probably an astrophysical reason for that, but that's TBD.
Last question: is the ALMA data field sufficient that didn't just get unlucky with where you thought the black hole would be? Like, could it be within some margin of error that is outside the ALMA?
Well, so the fast stars identify the center. Within they have to to keep them bound to the cluster, it has to be within about an arcsecond radius. Oh, okay. So we have that's sufficient. Yeah. We can confidently say there's no source that's consistent, unfortunately, with being there at the center. There was actually like a 2.5 sigma radio source in the previous radio data that was like 30 hours of ACA time. And they just published this 250 hours of ACA time paper, and they detect nothing as well. So it's really sad.
There before.
Yeah, like, we'll invest 10 days straight of observations and then get 0 results out.
The grad student who did those observations probably learned a lot about interferometry.
Yes, no doubt, that's true. Okay, so
school kids.
So this isn't the only IMVH candidate that we have in our local group. There are globular clusters in Andromeda where people have published dynamical estimates. I would say they don't meet this high level of, they're not as high precision of measurements. They could be stellar mass black holes rather than new mass black holes. But this paper from 2022 from my former student, Renuka Pachetti, found a black hole in M31's most massive cluster that's around 10 to the 5 solar masses. And in general, there's some indirect evidence that that massive black holes are fairly common in these brighter clusters around galaxies. And that indirect evidence is that their velocity dispersions, their integrated velocity dispersions, are higher than we'd expect based on their stellar populations. Using that information, my former postdoc, Karina Vogel, predicted a fraction of sources that are likely to have central black holes. And the point of this is showing the number of current galaxy nuclei and stripped galaxy nuclei, things that we think are probably UCDs with black holes or star clusters with black holes in them. And you can see that at this low mass end, where we have hatch, because it's very uncertain, it's very likely that the total number of stripped galaxy nuclei is higher than the present day number of galaxy nuclei. Another way of putting that is that things like the progenitors like Sagittarius, the Sagittarius galaxy and Gaia Enceladus, there's more things that have fallen into Andromeda and the Milky Way than are presently in the local group at that same stellar mass. So it's likely, I would say, that stripped nuclei outnumber present-day nuclei, dwarf galaxy nuclei, and therefore this is actually the best place to search for these IMBHs. And if we think about just our local group as a census of what black holes might be like, I put down little dots here for these black hole detections, Omega Cens down here, and then there's some gray dots of things that are maybe, I would say, less confident detections. And there's something like 2 to 4, less than 10 to the 5 solar mass black holes in the local group. And this suggests that the black hole mass function, which is what this plot is showing, really does not truncate at low masses. It seems to at least go down to roughly 10 to the 4 solar masses. And I think that's very good news for future gravitational wave detectors, which are going to be focusing on that kind of low mass IMBHs merging as a potential signal. Okay, so that's the end of that part of the talk. Okay, I'm going to tell you a little bit about Omega Cen star formation history. So Omega Cen has really, really weird stellar populations. There are extreme helium and C plus N plus O variations, meaning the carbon, nitrogen, and oxygen are all enhanced relative to solar scaled abundances. And that makes it very hard to derive absolute ages. And there's been significant controversy about what the range of ages is. Between 0, people have said that there's no spread in ages, to greater than 4 gig years as a range of ages. And the most sensitive part of most age-sensitive stars are these subgiant branch stars. In the cluster, everyone knows, the main sequence turnoff is where it tells you something about the age. And these stars on the subgiant branch are the ones that are most age-sensitive if you have a metallicity estimate. And so from our data, we have metallicity estimates for about 8,000 of these stars, subgiant branch stars, and we can use those metallicity estimates to get better age estimates. And by using the right HST filter combination, we can limit how uncertain the helium abundance variations make our measurements. And so basically what's shown in this right-hand plot is the red lines are the solid lines are the helium normal stars, and the dashed lines are helium enhanced. And in this filter combination, they fall pretty close to on top of each other. So they're close enough that helium variations aren't a significant contributor to our uncertainty. So we're able to measure individual ages for 8100 subgiant branch stars. This is the age metallicity relation in this cluster. And you can see there's a pretty wide range of ages. So we confirm that there's a wide range of ages. The orange line here is the age metallicity relationship derived from globular clusters that were part of Gaia Enceladus. So there's a bunch of globular clusters that have been identified as likely came in with Gaia Enceladus, and they have this orange line as an age metallicity relationship. So if clusters were forming in Gaia Enceladus and then falling in to the center of the galaxy, you might expect to see them along that line. So there's some pretty interesting things here. The most notable thing is there's this pretty clear lower boundary that seems to be kind of bimodal. You can actually see the bimodality in a couple of these histograms on the left-hand side here. So it suggests that there's multiple populations, one of which is kind of a linear feature in this diagram, the other one which is a little bit more of a cloud. This more metal-rich one at a fixed age is actually the one that's consistent with the guy in Enceladus clusters. The metal core stream, this kind of feature like this is actually the type of feature we expect for a self-enrichment scenario. So this all kind of looks like, okay, great, we have stars that are forming in the cluster, and we have stars that are forming in the galaxy. The confusing thing is this is backwards from what you'd expect. Okay, so at a given age, the center of the galaxy has lower metallicity than the rest of the galaxy, if that's the scenario that you're invoking. And that's really confusing because generally we see metallicity gradients rising to the centers of galaxies in the gas. So the centers are typically the most metal-rich parts of the galaxy. So very challenging to interpret, but clearly a feature that exists in our data. Another cool thing that we can do by combining our HST photometry and our spectroscopy is we can derive helium abundances. And the way that we do this is we use this thing that's often called the chromosome diagram. It's just a color diagram. Italians come up with weird names for things. They call it a chromosome diagram and stop calling it that too. Anyway, this is a 3-color combination, and it highlights objects that have deficits in this 336 filter relative to their 275 and 435 filters. And that is where there's a nitrogen band. So these objects that are up here are nitrogen rich. The other thing, and so you can see that this vector, red vector, is a nitrogen vector that's expected from abundance variations that we measure from high resolution spectroscopy. And this blue vector is what we expect helium to do on this diagram. You can see that it moves things to the left. Okay, so at a given metallicity, the fact that things are upwards, that's nitrogen. The fact that things are moving to the left, that's coming from helium. And it's not just a little bit of helium. It's more. So Omega Cen is about 3 million solar masses. More than 200,000 solar masses of the material in Omega Cen were converted to helium during its formation. It's an incredible amount. 7% of the mass of the cluster was turned into helium during the formation of the cluster. And that fraction keeps rising towards higher metallicities. And so at high metallicities, almost all the stars are helium enriched. At low metallicities, it's a small fraction. So there's this, and here you can see there's a little bit of a rise at the lowest metallicities in the difference in helium abundances, and then it kind of levels out. And we see high helium abundances for all of the stars. So this is the helium fraction, right? So the primordial helium fraction is like 0.24. We're adding plus 0.15 to that. So we're almost doubling the amount of helium in these stars. So these are really extreme helium-enriched stars. There really are no stars in our Milky Way other than the ones in Omega Cen that are like this. So these are unique stellar populations. So we can actually try also using our Muse spectra to measure abundances. So there's been a lot of efforts in recent years to use machine learning to use high resolution spectra and then translate the labels from that high resolution spectra to lower resolution spectra. My postdoc Primordial has been working on this, and we're able to get accurate sodium, magnesium, and oxygen abundances. And the orange line here is those helium-enriched stars. The blue line is the helium-unenriched stars. You can see now we can track those abundances and how those are varying from metallicity. Putting this all together in a single formation picture has so far not proven easy. There's like certain things just don't fit together at all, kind of like I was talking about with the 2 different age metallicity relations. So, but I wanted to finish this. I just have one more topic that I want to talk about briefly, but I wanted to finish this by just mentioning that these things might be connected. The IMBH and the abundance variations may be connected, and the connection would be through some formation mechanism. We talked about how the C black hole formation mechanism isn't known yet, One possible mechanism is formation of a supermassive star during the formation of the cluster, where stars keep bombarding into a central star. They keep that puffed up. They stop it from blowing up as a supernova. You can build up a star potentially of many thousands of solar masses this way. And during its lifetime, it's polluting its environment with enriched material that's enriched in CNO cycling and hot hydrogen burning. And that could potentially link these two observations, why we have these unique star populations and this black hole at the same time. Okay. I'm going to talk just a little bit about black holes in Omega Cen. We expect there to be around 10,000 black holes on dynamical models of Omega Cen. And this is an interesting question because we know that a lot of people think LIGO events come entirely from black hole mergers that are happening in globular clusters. And Omega Cen is our best possibility of finding the population, the parent population of these black holes. So Omega Cen is our most massive cluster. It has a high escape velocity. It should retain a lot of its black holes, but we have so far found 0. Okay, so there's been searches for binaries where we'd expect stars to pair up with black holes, and so far no radial velocity binaries have been found. Some astrometric binaries have also been found, and so far 0 black holes found out of expected population of 10,000. So we have been trying to figure out if there evidence, direct evidence for stellar mass black holes in this OMEGACat data, not dynamical evidence, but direct evidence. And we've been working on microlensing, which is possible, and also by looking for binaries. And this is all work that's been done by Utah undergrads. They've been amazing. We found a bunch of binaries. I'm running out of time, so I'm going to just go to the most exciting one, which is this highest mass object here, which we think is a black hole. This object was actually detected in the previous astrometric binary population, but they inferred a mass that was much lower than we're finding. And the thing that's changed is that we have an extra decade of measurements that we processed. And that's, you can see these purple measurements right here, which don't match up with this arc of measurements. This is colored by the year. So this object is clearly accelerating. It's got a curved track on the sky. But then you can see that in between, it does some sort of hitch right here. And that hitch ends up being, it's going through its pericenter passage. And that means that we're able to constrain its mass a lot better. And its mass is 6.5 plus or minus 2 solar masses. We still are not observing the whole orbit, so we have some degeneracy between our inferred proper motion and mass, but that degeneracy actually leads us to higher masses. It's very clearly a black hole candidate. One interesting thing is that this binary system is soft, meaning it shouldn't live the lifetime of the cluster. It should be destroyed by interactions with other stars in the cluster, and yet it's there. And this is the first black hole detection, first stellar mass black hole detection in Omega Cen, and the third black hole detected in a globular cluster. So it's a very rare object and definitely interesting. That is all I have. 2 black holes, Omega Cen.
So a couple questions. First, does the fact that recoiling black holes do not seem to be enormously, recoiling active black holes do not seem to be very abundant, place limits on your theory, hope that most of the intermediate mass black holes are stripped nuclear star clusters? I mean, if that simulation you showed where it kicks itself out and maintains cohesion is true, I mean, they don't all have to be active, but presumably some would be in the aftermath of a merger. And there's not many recoil candidates right now.
Yeah, so I mean, the fraction of all black holes that are active is very small. So it's like 1 or 2% of all black holes are accreting at more than 1% of Eddington. And so I do think that presents a challenge by itself, even without, and presumably getting kicked out of the environment, the nuclear environment means that you're less likely to be actively accreting because there's only a very short lifetime where that mass would stick around accreting. So I don't think that, what I would say is I don't necessarily think we know the black hole occupation fraction. I certainly think that there's got to be systems where things happen, and we're not going to. So, for instance, M33, the Low galaxy, doesn't seem to have a black hole. Its upper limit, dynamical mass upper limit, is pretty low. And so, my interpretation there would be that it probably doesn't have a black hole, and that might be because it used to have one and it got ejected, or it might be that it just never formed one. So I don't know. It's pretty hard to turn. I think there's so many selection effects with the recoiling and the binary, the dual supermassive black holes, that it's really hard to turn that into constraints on models.
And then my second question was, you have pretty good limits on the upper and lower bounds from your fast moving stars in the center. And then you mentioned earlier on that you weren't quite sure which merger that Omega Cen might have come from.
Yeah.
But there's obviously, there's correlations between black hole masses and galaxy masses. So does that help? Does your new constraints on the black hole mass help you say, well, it had to be a satellite with a certain stellar mass?
Yeah, I think, I guess I would say that because of the fact we don't know exactly when the merger happened, and so we know the M sigma relation probably changes with redshift. I would say that we don't really know how exactly it changes with redshift. So that, I think, makes it hard to do that. I think actually the nuclear cluster itself may be a little easier to use because there's also nuclear cluster galaxy mass relationships, and that is consistent with Gaia Enceladus. So the estimated mass of Gaia Enceladus is a little over 10 to the 9, and that's consistent with having a few million solar mass nuclear cluster. But yeah, it's definitely a good idea. And if we had, if we kind of even take the negative test, if it is Gaia Enceladus, we do know roughly when that merger happened. It was about 10 billion years ago, 9 billion years ago. And then we can, if we were able to get a good M sigma relationship for then we would, yeah.
It's just that easy.
I just shook my head.
Yeah, that's only redshift 2, right?
Yeah. Within an order of magnitude, I'm sure.
Yeah.
You mentioned at the beginning TDEs, and that is quite literally the smoking gun of whether there's a black hole here.
Yeah.
Do you have any guess as to how long, even with Rubin, we'd have to stare at Omega Cen to see a TDE happen?
Yeah, so we do know the TDE rate. We've calculated the TDE rate for Omega Cen for an IMDH of say 40,000 solar masses, and it's 10 to the minus 8 per year. So, it's a lot of grad student lifetimes. There was, until just recently, an off-nuclear TDE detected, published by Yuhan Yao, and so that was the first off-nuclear TDE. And the reason it was found was it was close to the center, and so it didn't. In general, the filters that have been used to find TDEs have required an existing galaxy there. My feeling is that we're going to end up finding a lot of TDEs, even though so even if each of them is 1 per 100 million years, there's definitely more than 100 million of these objects in our depth that we are observing. So I think we'll definitely observe some more. They've already observed one, and it seems to be in a massive cluster. So to get a TDE, unlike the recoiling thing, to get a TDE in an off-nuclear black hole, really the only way is to have a strict nuclear cluster because you need a lot of stars here.